First, we'll understand that what is the atomic emission and what is the atomic absorption. So, in this figure number A, if you see that the sample is excited. In this case, it may be excited hydrogen atoms using the external energy. So then it will pass through the prism and it will be separated in different wavelength, which is called the spectrum, and it will be detected by the photographic plate. So in the atomic emission, you will see some lines, and in between whatever black is there, that means there is no spectrum with wavelengths. For atomic absorption, in this case, figure number B, a white light source will be there, and from there, this white light source will absorb in the sample, and whatever the remaining wavelength is there, that will go through the prism and it will be detected on the film or detector, and it will come like this spectrum. So you can see that where is the wavelength is absorbed by the sample, that will not come in this way in the prism, and ultimately in the spectrum that portion will be the black. So these two cases, these all are the slit. Slit means from slit the light will pass. And so these recorded all absorption spectrum also is called the line spectrum, and the photographic negative of the emission spectrum, it is called the absorption spectrum, is the photographic negative of the line spectrum. So in this case, if you see that where it is the specific example of the hydrogen, so when it is the emission, then this portion all are black, but here it is the color, so it is just like opposite. And in left side, if you see, for absorption, atomic absorption spectra, this left side portion is a black, but for the above case, the emissions spectrum, left side is the colored. So it is opposite to each other for the same sample. Here, something you have to know, the speed of the light depends on the nature of the medium. And when it will pass through the medium, then the beam of light is deviated or refracted from the original path as it is passes through the one medium to another. So if you consider the prism, in this case, if the white light is passed through the prism, then shorter wavelength bends more because it will deviate more than the wavelength having the longer wavelength. So we have to remember that through prism pass some light, white light, then whatever the shorter wavelengths, that will deviate more, and whatever the longer wavelength, that will deviate less. So the ordinary white light consists of the waves of all the wavelengths in the visible region. That means this white light is consists of the number of the colored bands, and it is called the spectrum. The light of the red color we know it is the longest wavelength, and so it will deviate least. And the violet light, whose wavelength is shortest, then it will deviate the most. Now, the spectrum of white light ranges from violet. That means it has the shortest wavelength, and it is the 7.50 multiplied by 10 to the power 14 Hertz. And red, which has the largest wavelength, so its value is the 4 multiplied by 10 to the power 14 Hertz. So this spectrum of white lines spread from the violet to red, and it is called the continuous spectrum. Why continuous spectrum? In between no gap is there. Because violet, from the left side, if you consider, violet almost merges to the blue, because just next higher wavelength is the blue. So violet will merging with the blue, and blue, it will merge to the green, because green has comparatively longer wavelength than the blue, and so on. It will continue up to red. And so the similar spectrum you can see in the rainbow in the rainy season in the sky. So visible light is just a small portion of the electromagnetic radiation. In previous class, we discussed in detail. Who did not see that class, please see that class, then you will understand. When electromagnetic radiation interact with the matter, then atoms and molecules may absorb the energy and reach to a higher energy state. In atomic emission spectrum, it will happen like that. With higher energy, so these are in the unstable state. So they want to release that energy to come back to their lower energy state. And that's why these atoms and molecules emit radiation in the various regions of the electromagnetic spectrum. So the spectrum of radiation emitted by a substance that has absorbed energy is called an emission spectrum. The first figure, figure number A, list of the atoms, and it is molecules, and sometimes it is in the ionic forms. They have absorbed radiation, are said to be excited. That means when they absorb the radiation, then we'll tell that these are in excited state. So to produce an emission spectrum, energy is supplied to a sample by heating it or irradiating it, and the wavelength, frequency also another derivative of the wavelength of the radiation emitted, as the sample gives up the absorbed energy, and it will be recorded by the detector. An absorption spectrum is like the photographic negative of emission spectrum. Whatever I discussed, a continuum of radiation is passed through a sample which absorbs radiation of certain wavelength. In that figure, I already described in the figure number B, it is happening. The missed wavelength which corresponds to the radiation absorbed by the matter, then it will leave the dark spaces in the bright continuous spectrum. Because which wavelength is absorbed, it will not come to the detector, so that portion definitely it will be the black space. And this whole things, the study of the emission or absorption spectra is referred to the spectroscopy. The spectrum of the visible light, what I already discussed, was continuous as all wavelengths. That means red to violet. Violet has the shortest wavelength and red has the longest wavelength of the visible light. The emission spectra of atom in gas phase, on the other hand, do not show a continuous spread of wavelength from red to violet. Rather, they emit light only at specific wavelength with dark spaces between them. Such spectra is called the line spectra or atomic spectra because the emitted radiation is identified by the appearance of bright lines in the spectra. And this happens for the hydrogen in the figure we have seen. So now the line emission spectra are of great interest in the study of the electronic structure. Each element has a unique line emission spectrum, and with that it is the unique for each element. So with that we can identify that element. The characteristics line in atomic spectra can be used for the chemical analysis to identify the unknown atoms in the same way as the fingerprint is used to identify the people. Nowadays, everywhere, if you enter, I think even college, university, also it is there, fingerprints is there. And with fingerprints, only you can enter. And these fingerprints will identify that particular people. And same case, the unique line spectrum, it is unique for each element. And with that line emission spectrum, we can identify the elements. The exact matching of the lines of the emission spectrum of the atoms of a known element with the lines of the unknown samples quickly establish the identity of the latter. That means whatever already line spectrum is there for the particular elements, suppose for hydrogen, and if some unknown sample is there, unknown gas is there, if you get the line emission spectrum, then if it is matched, then we can tell that whatever the unknown samples, unknown gas is the hydrogen. So now the question will come that who invented this? Who discovered this? German chemist Robert Bunsen. Bunsen is very famous, Bunsen burner. If you enter the lab, then you will see that this is the Bunsen burner. And that naming has come to the great German scientist Robert Bunsen. And he is one of the first investigators to use the line spectra to identify elements. What he has done, elements like rubidium, cesium, thallium, indium, gallium, scandium were discovered when their material were analyzed by spectroscopic methods. What is the spectroscopic methods? Both atomic emission and atomic absorption is the In total, it is called the spectroscopic methods. The element helium was discovered in the sun by the same spectroscopic methods. Sun has a lot of heliums, because you know that hydrogen atoms are fission to convert to the helium, and these helium elements in the sun was discovered by this spectroscopic method.